Okay, this screencast covers dark matter. Dark matter is something that is different from dark energy. Dark energy is covered in a different screencast. The first hints of the discovery of dark matter go back to the first half of the 20th century with this man here, the American astronomer Fritz Zwicky. Fritz Zwicky's research was concerned with measuring the velocity of galaxies within galaxy clusters. He conducted these measurements back in the 1930s and the 1940s. What he measured with respect to the velocity of galaxies within individual galaxy clusters is that the velocities themselves are actually larger than what can be accounted for based upon the mass of the cluster that is visible. Okay, right here is a nice picture of a nearby galaxy cluster called the Coma Cluster. The Coma Cluster consists of several hundred to a few thousand galaxies contained here within this volume. What Zwicky was concerned with, for example, was measuring the speeds of these galaxies as they move within the cluster based upon their mutual gravitational attraction. Here's basically the problem, if you will, that Zwicky measured. Okay, the members of a galaxy cluster move because of their mutual gravitation, their gravitational attraction, that is. What Zwicky discovered, however, is that the galaxies are actually moving faster than what can be accounted for based upon the mass of the cluster causing the amount of gravity that is present. In other words, the galaxies are moving faster than what can be accounted for based upon the mass of the cluster itself. Now, one possibility is that he just happened to observe a galaxy cluster while it was in the process of breaking apart. That might be the case if you just discover this in one cluster, but Zwicky discovered the exact same effect in every galaxy cluster that he observed. He observed that the galaxies are moving faster than what can be accounted for based upon the visible mass of the cluster itself. So Zwicky hypothesized the following. He hypothesized that the mass of the cluster must actually be much larger than what is actually visible to account for all of the gravity that we're seeing here with the speeds of the galaxies within the galaxy clusters. So this hypothesized something, this unseen matter, if you will, that's causing all of this gravity, he gave it a name. He referred to it simply as dark matter. If you work out the measurements, for example, of how much matter must be present in order to cause all of the gravity associated with the motion of these individual galaxies, it turns out that more than 95% of the matter is not being observed in our telescopes. 95% of the matter is dark. Okay, now we move a couple of decades to the 1960s to the American astronomer Vera Rubin. Vera Rubin discovers the same dark matter that Zwicky did, but she does so in a different way. Rubin's research was concerned with measuring the velocities of stars in the disks of spiral galaxies. The velocities that she measured are greater than what can be accounted for based upon the visible mass of the galaxy. So, for example, take a look at this slide here. Take a look at the second diagram. We have right here the center of a galaxy, for example, and then stars A, B, C, D, and so on. According to Newtonian gravitation, as you move further and further away from the center, then the speeds of the stars within a galaxy should decrease according to a graph that looks like this. Here at the top, however, for example, if a galaxy behaved like a phonograph record and was kind of like a solid object, then we would find for stars A, B, C, and D that we would plot a graph like so, describing their orbital speed as a function of distance from the center. This right here, however, the second portion of this graph, is what is expected based upon Newtonian gravitation. However, when Vera Rubin made her measurements of the speeds of stars in individual galaxies, here's what she obtained. Once again, here on the left-hand side is what we would expect based upon Newtonian gravitation. However, on the right-hand side, she measures, for example, orbital speed as a function of distance. It looks very similar to that of the phonograph record on the previous slide. The only way to account for a graph like this is that there must be much more matter that is present within a galaxy than what we can actually see to cause all of the necessary gravity to result in a graph such as this. Once again, this hypothesized something called dark matter. So dark matter was discovered essentially independently by two different astronomers separated from each other by a couple of decades in observing different phenomena. Zwicky discovers dark matter based upon the motion of galaxies within galaxy clusters. And then within individual galaxies themselves, Vera Rubin makes the same discovery based upon the rotational speeds of the materials in the disks of spiral galaxies as you move further and further away from the center. Okay, here's kind of like a map, if you will, of the amount of dark matter that must be present in an individual galaxy cluster, kind of constructed like so as a halo. Halos of dark matter surround galaxy clusters, and in individual galaxies, as discovered by Rubin, must be enveloped by halos of dark matter as well. As I mentioned earlier, measurements show that more than 95% of the matter in galaxy clusters, for example, is dark. The majority of the universe is made of material that we cannot see. We could actually map out very precisely within galaxy clusters how dark matter has to be distributed. We do so by using gravitational lenses. I describe gravitational lenses and other screencasts quite extensively in my lectures on general relativity. So in this particular scenario, we have a foreground galaxy cluster like so, and then we have way in the background an individual galaxy, and then right over here is the Earth. And then as the light from this galaxy passes by the galaxy cluster, the amount of matter that is present here bends space and time enough, resulting then in the light being curved in this direction, such that it then ultimately reaches our location here on the Earth in the Milky Way. So when we sit here on Earth and then look at this galaxy cluster, we then see multiple images of an individual galaxy surrounding it, the galaxy in the background. That is, for example, like so. So here's an enormous cluster of galaxies in the foreground, and then in the background it is an individual galaxy, and the light from that galaxy is being lensed. That's what you see here with these individual arcs, like so, going all the way around this galaxy cluster. You can then use the details of these multiple images of the single background galaxy to map the distribution of dark matter that must be present as a halo within this galaxy cluster. That's what this photograph is right here. The blue material that you see right here is actually a map of the distribution of dark matter that must be present here within this galaxy cluster to cause the gravitational lensing effects of a background galaxy. Okay, now what is the dark matter made of? Well, it might be made of ordinary matter. However, there's just not enough of this ordinary matter to account for 95% of the universe not being visible. So, for example, it's been hypothesized that basically the dark matter might be made up of neutron stars. But neutron stars are formed from the deaths of very massive stars. Where are all of the neutron stars that is necessary to make up 95% of the missing mass of the universe? The universe is too young, basically, to make all of those neutron stars. Same thing with black holes. Maybe all of the dark matter is made up of black holes, but once again, you have to make all of those black holes. How do you form them? The universe is too young for that to occur. Another hypothesis is that the cooled down remnants of white dwarfs, what are called black dwarfs, might make up the dark matter. But once again, the universe is actually too young to form black dwarf stars, so then therefore black dwarfs cannot be the dark matter. Same thing with what are called brown dwarfs, by the way. Brown dwarfs are kind of like an in-between, if you will, between planets and stars. We have observed brown dwarfs, for example, nearby, but there's not a lot of them. So then therefore the missing matter cannot be made up of all of these individual brown dwarfs. There's just simply not enough of them. We don't see enough of them nearby, for example, to make up all of that mass. Same thing with ordinary planets and ordinary rocks and stuff like that. There's just simply not enough of this material to make up 95% of the universe. All right, so then therefore, what could the dark matter be? Well, there are a few candidates, a few exotic candidates, if you will, that is not ordinary matter. It's been hypothesized that the dark matter may be a piece of the standard model of particle physics, a type of object that is called a neutrino. We have observed neutrinos, for example, in plenty of particle collision experiments in particle accelerators, but neutrinos are not very massive. So they do exist in large quantities, but it's not enough mass to make up the missing mass of the universe. Another possibility is that the missing mass might be a leftover remnant of the Big Bang called a cosmic string, which is kind of like a crack, if you will, in the fabric of space and time. Cosmic strings have been hypothesized, but we have never seen any evidence of their existence, so then therefore cosmic strings are probably not the dark matter. Another possibility is called modified gravity, or MOND, modified Newtonian dynamics. Modified gravity basically hypothesizes that we don't really understand mathematically how gravity works on a large scale. So then therefore, if you take Newtonian gravitation, for example, and mathematically tweak it a little bit, you can then have it account for the missing material. Same thing with general relativity. If you tweak it a little bit, you could have it account for the missing material. However, there's no physical reason for us to make these mathematical tweaks. So even though MOND does have its supporters within the physics community, it is largely thought of as more or less a fudge factor, basically just taking existing mathematics and tweaking it a little bit so it fits what we see. However, probably the most likely candidate for dark matter, at least as far as we know right now, is a hypothesized continuation of the standard model of particle physics, something beyond the standard model of particle physics called a WIMP, a weakly interacting massive particle. WIMPs are hypothesized to exist as a continuation of the standard model of particle physics, but we have never seen any evidence of their existence in any particle physics experiments. Very detailed searches for WIMPs have been conducted over the last 15 years. The way that you would find them is basically to take a tank of very pure material, in this case xenon, bury it underground so it's shielded from cosmic rays and the solar wind and so forth, and then, however, every so often, one dark matter particle, a WIMP, a weakly interacting massive particle, will interact with the atoms that make up the material within your tank. And so then therefore you watch for those interactions very carefully with this tank of material underground. These types of detection experiments of dark matter candidates have been conducted extensively over the last 10 to 15 years with an ever increasing degree of precision, but no dark matter detection experiment has been successful thus far. So because of our failure to detect dark matter and our failure to explain it adequately, physics has kind of run into a big problem. We don't know what the dark matter is. We have some exotic candidates, but we've never seen any evidence of their existence. But we do know that the dark matter has to be there, because how do you account for all of the gravity that we see, yet we can't see the material? So dark matter is considered to be a major problem in astrophysics and physics in general. Probably whoever it is that solves the problem of dark matter will probably change the nature of physics as we understand it today, and will undoubtedly be up there with Albert Einstein and Isaac Newton and perhaps a couple of other people. So let's see what happens as the 21st century goes forwards. Let's see if humanity is able to figure out the conundrum of dark matter.